So thank you very much. And I want to thank first rism for having us, organizers for organizing this conference, right? And Thomas started with this line actually, but he missed a couple of conferences. It was the one was on profiling groups still in Cortona that was organized by Otto Kegli and Andrea Caranzi, and then it was one in Vienna, all right, as well. In Asia Institute, so there was the line was more dense, and then it was all right. But well, this is not a better word. Right. Anyway, right. So I want to start. I chose this title actually because since you mentioned Lubotsky, actually 40 years ago, he published a paper with exactly this title. All right, and it was the first paper on the subject. All right, and the title was a bit ambitious, right? But nevertheless, it developed during 40 years. So my sort of objective to show how it was already developed and where still to go. But I'm not going to cover all aspects of combinatorial group theory because I mean I'm limited in time, and therefore I will look just at the maybe my talk will have geometric flavor, but not meaning for proper groups geometric flavor, but geometric flavor when we have sort of appealing to something that is already known in the paper, in the abstract world. All right. So the paper that I mentioned of Lubotsky on combinatorial theory of proper groups, he had 3 results, and they were all about free proper groups. All right, he proved Marshall-Hall theorem version of the Hausen theorem, and plus he proved that automorphism group of free proper group is virtually torsion free. That was basically 3 results of that paper, and it was only about free groups, free proper groups, right? And of course, combinatorial theory is not sort of about free groups, right? It is about other things. So I want to start with the 2 basic constructions which appears in combinatorial group theory. All right, it is 2 basic constructions in combinatorial theory. It is amalgamated free product and H-in extension. All right. So what are the constructions? All right. Amalgamated free product. The data is the following. We have 2 groups, G1 and G2. All right. When we have common subgroup H, all right, and we just make free product of 2 groups G1 and G2, and then we amalgamate in H, meaning that we have copy of H in G1 and copy of H in G2, and we just identify them. Right. So you can consider also this as a push out, but in principle you have this presentation which explains everything exactly what I told. And the second construction is H-in extension, which is named after Higman, Neumann. Right, and it is the data is the following: you have a group, you have a subgroup of it, and another embedding of H into G. All right, and then you also it is given by presentation. You have then it is generated by G by another element. All right, extra element T, which is called stable data. All right, and then again you have this relation that conjugating by T is the same as this another embedding of H in G. This is 2 basic constructions, and combinatorial theory of groups is actually practically about this, because there are 2 things which historically was developed in this direction. First thing, you care about subgroup, how to describe subgroups of this construction, right? All right. But before that, I want to say that free products actually and free groups, right? There are particular cases of this construction. So we are not throwing out free groups that Lubotsky started with, but when we think about how to describe subgroups of this, right? Then first, it was sort of by playing words, because these things were can be described by every element as a word. But then came Basser theory of groups acting on tree, and this is exactly what solved the problem. All right, that the subgroups of this construction are described by means of groups acting on trees. All right. The second story is actually about overgroups of these constructions. So if we have this construction, for example, as a subgroup of finite index in given group, right? We want to think about, to understand the structure of the group, and this is comes from Stollings, right? It is famous Stollings theory of n's solves basically the story, and the second ingredient of the big theory, which is called Basser theory, right? Plus Stollings theory that deals with these two problems, all right? And my direction of the talk was is actually what how sort of we deal with the problem in the Pro-P case, with these problems in Pro-P case. So we can go to next slide, all right? And then we state first this two theorem of Stollings. So we're doing of overgroups. So if we have virtually free group, and when I say virtually, I mean subgroup of finite index, all right, with certain property that we are talking about. So Stollings theorem says that virtually free group splits as an amalgamated free product or an extension of a finite group. And the second theorem of Stollings is generalization of this. So actually, historically, this is a corollary of this, right? But nevertheless, I stated it separately because there are two different theorems, right? So the second theorem of Stollings, and I a little bit reformulate actually the original result, right? But nevertheless, it is exactly this. If we have finitely generated group containing subgroup, right, that splits as a non-trivial free product with amalgamation or an extension, right? Of a finite group, then G also splits either as a free product with amalgamation or an extension of a finite group. Right? That's two results, and I now come into the Pro-P case and will treat these two results in the Pro-P case. So what do? We first define the constructions, and constructions in Pro-P case defined exactly the same way. Right? So we just take the same presentation in both cases, in both data, right? So but only groups are Pro-P and all homomorphisms are continuous. So we are now in the world of Pro-P groups, and we're doing everything in Pro-P case, in the category of Pro-P group. Right? The rest is the same. But there is a small problem here. Because in the abstract situation, the basic blocks, like G1 and G2, they always embed in free amalgamated product. In Pro-P case, it is not always the case, all right? And we say that the amalgamated product or chain extension is proper if it is the case, if it is embedded, and it is not doesn't restrict generality because we always can actually replace original group by the images in the free amalgamated product or chain extension, and then we get this embedding. But also, following geometric group theory terminology, I will use the word splits. All right. So I would often say that group splits as amalgamated product or chain extension. Why? Because the word splits means already that actually my building block are subgroups of a given group. Right. So I don't need then to say proper, not proper, and so on. All right. Okay, so after this, I can come to the Pro-P version of the Stollings theorems, and the first theorem was proved by Wolfgang Herford and Spica. All right, and it says exactly what is in the abstract case. Stollings theorem says that virtually free Pro-P group splits as an amalgamated free product or an extension of a finite group. But this is now in the category of Pro-P groups, right? All right, and the second statement was proved by Thomas Weigel and Spica, right? And again, This is now in the category of pro-P groups, right? But again, the statement is absolutely the same. All right? That finitely generated pro-P group contains a subgroup of finite index, right? Which splits as a non-trivial free amalgamated product or H extension of a finite group, also splits over finite group as a free product with amalgamation or H extension. Okay, right? But now I want to say that we actually, in pro-P case, can go beyond decomposition of a finite group. Right? So this is two recent theorems that was proved by my student Mateus Aguiar, right, and the speaker, and it says as follows. Now we have pro-P group, right, and splits again as amalgamated product or H extension, right? I do them parallel. You see, this amalgamated product, this H extension, but basically it is the same statement, right? It splits, but now our amalgamated subgroup or H extend or associated subgroup is not finite. It doesn't have to be finite. Nevertheless, result is still true, right? Right? Providing, right, that our building blocks do not split further over some subgroups of K, right? That they are unsplittable, right, in our environment. So if H1 and H2 are indecomposable, right, over any conjugate, indecomposable means that they do not split as amalgamated product H extension as well, then our overgroup splits as amalgamated product or H extension here. All right, and I never seen such a statement in the abstract case, so that's why I say that in pro-P case it looks like that we can go beyond what Stallings originally proved in the abstract case. Okay. Now I want to say a little bit about this indecomposability condition. How restricted is it? It is not very restrictive. We have many groups, right, that satisfy this condition, right, and especially groups that are actually favorable in this audience, right? So all FAB pro-P groups, right? FAB means that every open subgroup has finite abelianization. So practically all analytic pro-P groups, right, have this property, and of course just infinite pro-P groups like Grigorchuk groups, Gupta-Sitke group, Nossingen group, and so on. They actually do not split at all over any group. All right, and as amalgamated product, and therefore the theorems of the previous slide really applies to those situations where groups are FAB. All right, and this property important. All right, and I also want to mention the following: that in the paper of Claudio Condrebli, Ellipse Nobsch, and Matteo Svinacci, all right, they appear this kind of amalgamated subgroup over analytic pro-P groups as a in the study of generalized RAG pro-P groups. So they really, of course, we can take two groups, all right, having this property and try to make amalgamation, right? I mean, we always can do this, right? But they appear naturally here in that paper, right? And plus, they proved that the amalgamation always proper when we have amalgamated over uniformly powerful pro-P group. So we don't have to worry about properness or not properness anymore. All right. So there are many, many examples of this sort. That's what I wanted to say. So it is not very restrictive, this condition of indecomposability. All right. Okay. And now we come to the different story. How do we treat subgroups of this construction? All right. Now this Buster theory. So Buster theory, it says the following. It treats uniformly amalgamated product and H extension at the same time, right? And then we need a notion of graph of group. So what is graph of group? Right? Well, graph of group, it is something what is written on this picture. We have a usual graph, and then on every vertex sits a vertex group, on every edge sits an edge group, and then we have this, how do I do it? Where's the pen? I see. All right, so I don't need it. All right. So we have these two embeddings from one group to another for every edge, right? That I will call boundary homomorphisms, right? And then for any of this construction, we can define fundamental group, which is whose presentation is the mixture of presentation of free amalgamated product or H-n extension. It is really encoded here. All right, that we have here maximal subtree, all right, and then if H in the maximal subtree, then this additional element is trivial, so we don't have anything, right, and we have sort of amalgamation relation, right, and if this H is outside of the maximal subtree, then we have sort of H-n extension relation. So this how a fundamental group of graph of group is defined, and then I should have. It doesn't matter anymore, or you need it for historically.
Okay. And
yeah. All right. And we really have this amalgamated free product tangent extension in very simple cases of graph of group. All right. It is when we have just one H and two vertices, right? Then our fundamental group is exactly free product with amalgamation of two vertex groups with an H group. And when we have this H and an extension, we have H and extension when we have just graph that consists of one loop. All right, so that's how we recuperate into this. All right, and then I come to the sentence that our fundamental group is, in fact, is a successive sequence of free amalgamated product and H-n extension. So how it goes? Let me go to the next previous slide and show. For example, if we take concentrate on this H, all right, on this H. Oh, I have to put some, yeah, like this. This one, yeah. If I take this, concentrate on this H, then actually this fundamental group is really amalgamated free product of this vertex group, right? And of the whole, this guy. All right. So we have this group, then fundamental group of this graph, right? And then we have free product with amalgamation of these two groups, amalgamate on this H, right? Okay. Now, if we... No? I just wanted to cancel this.
You want to cancel it?
No, I just want to use my finger freely. Yeah. All right, if you... All right, and yeah. All right. And having this, how do we decompose this graph in H-n extension? We concentrate on this H. All right. So I put here on this H. So we delete it, right? And then we have this fundamental group of this graph of group that would remain, right? And then we get this. No, I have to cancel it. Yeah. Like this.
Yeah. And now press cancel again, please. Or you can cancel.
And like this. All right. And then we have this H-n extension of this graph of group, right? Along this associated subgroup. Okay. And main by a theory of Buster theory, for some reason it is. No. I think it's okay. It is visible, I think. All right. It says the following, that group G acts on a tree if and only if G is fundamental group of graph of groups where edge groups and vertex groups are actually stabilizers of vertex and edge groups of the group that acts on a tree. All right. And the important remark that in abstract case, if G is finitely generated, then T mod G can be assumed finite. Why? Because you can always find G invariant subtree with this property there. All right. Again, why? All right. Well, because every element of G is really can be written as a finite weight of generators. That's why. All right. And as a corollary, all right, we get a subgroup theorem, which is which was our aim. Our aim was to describe subgroup of free amalgamated product OH and extension. This subgroup theorem now states as follows. A subgroup of amalgamated free product OH and extension is the fundamental group of a graph of groups whose H and vertex groups are conjugate into H and G1 and G2 respectively. That's it. This is our description. Now, what do we do in Pro-P case? We need to define a profinite graph. So, profinite graph is easy to define. We just take inverse limit of finite graphs. That's it. Now, a profinite graph, we say that it is connected if it is inverse limit of finite connected graphs. So every finite portion of this becomes connected. All right. So this is not a problem, but we need to define a Pro-P tree. So we define then this the following way. Well, as we know that profinite graph is inverse limit of finite graphs, right? For finite graph, we can take our usual fundamental group, which is free on this number of our set of generators, gamma minus d, where d is maximal subtree. All right, and then we make Pro-P completion of it. If we have free group, we can have for Pro-P completion, we get a free Pro-P group. All right, but then this inverse system induces the inverse limit inverse system of our completions, Pro-P groups. Then we take inverse limit of this, and we call this fundamental group. And then if fundamental group is trivial, we say that gamma is a tree, a Pro-P tree. All right. Good. So we have already fundamental group of a graph, but we need to define. All right. And then what we have is the following: that in the abstract situation, we know if we have free amalgamated product and H in extension. All right. Then group acts on the standard trees associated to it. All right, because we have a theorem that well, I already mentioned that main theorem that fundamental group that group acts on tree if and only if it is fundamental group of graph of group, and amalgamated product H in extension is actually the particular cases of this. All right. And the similar construction of the tree, right, works for Pro-P case. If you have amalgamated free product H and extension in the Pro-P case, right, there is a Pro-P tree on which amalgamated product or H and extension acts, right? But what about converse? Well, converse is not easy. I wanted actually to do something that appears the next one, and I cannot do it like that. I have to press something like next slide. Where do you press? Plus?
You want to go to next slide?
No, the problem is that there's part of the slide which is missing here. I have to press it. Yeah, okay, this would do. Okay, right. So in the abstract situation, and the problem is that converse is false in general in the Pro-P case. All right. It doesn't split. Why? The problem is the following: if you have abstract graph, you can take H and cancel it. Just take it out from the graph, and then you have still graph. In the profinite case, it is not the case. You cannot take H out because you get not compact object. It is not profinite graph anymore, and therefore you lost your context. All right. So this is a problem, right? And I want to present theorem that for Pro-P case, and if we assume that G is finitely generated, then converse is true. All right. That if group acts on a property tree, then it splits really as a free amalgamated product or H in extension over some stabilizer of an H of T. All right. So we have this. All right, for finitely generated case. And this is good because then we can proceed with further development. Okay. Now, what do we need? We need then Basser theory of groups on a tree. If we have splitting, right, we need to generalize it as it was done in the abstract case. So we have to give a notion of fundamental group of a graph of property groups, which is pretty the same if gamma is finite, right? Right. Actually, graph of group, fundamental, and the graph of group is pretty the same even if gamma is profinite. But I will restrict here now to finite graphs of groups because it is then definition is easier, right? And plus, I want to assume that the groups is finitely generated, vertex groups are finitely generated. Then I plainly just can make a profinite, proper completion of it. And then I don't come into the details of what is different in the proper case, or how we should adjust definition. All right. But in principle, it is a fundamental group of graph of a group can be given just by presentation, the same presentation as in the abstract case. All right. But in the category of proper groups. Okay. So we have this definition. All right. And then the important examples are exactly those theorems that was proved by Herfen Speaker and Thomas Weigand Speaker. Namely, that finitely generated virtually free groups or finitely generated virtually free product then become examples of fundamental group of graph of groups. In this case, all vertex groups are finite. In this case, all edge groups are finite. Right, so they really describe in this manner. So they appear, this construction appear naturally, all right, as a description of virtually free property groups and all virtually free property products, all right, and then comes the questions of accessibility. So what is the problem? What is the question of accessibility? Well, suppose we have a group, right, and we split it as amalgamated product. Well, we split it amalgamated product, but then vertex group can split again as amalgamated free product. I mean, factors. Factors can split again, and then split again, and then split again. And accessibility asks whether this process stops, right? Whether this process terminates in finite number of steps, right? This is the question of accessibility, all right? But proper definition is the following: that our graph of group where we split has to have bound on the size. All right. The underlying graph has to have bound, and this bound is called accessibility number in my talk. I'm not sure whether there is a proper term for this, but in my talk it will be accessibility number because I'm going to mention it a couple of times. All right. And but of course the graph of group has to be reduced. What does it mean? You see, any group can be looked as a free amalgamated product because you can take G, amalgamate with G, the same G, right? And then, but this is not interesting because it is fictitious, right? Splitting, right? So the way to eliminate from graph of groups this fictitious splitting, right? You just say that every H, which is not a loop, right, has the following condition, that H group should be different from vertex groups that it is connected to, right, the extremities. All right, okay. Accessibility, and then I want to say that accessibility was studied by Don Woody in the abstract case, and he proved that every finitely presented group is accessible, but finitely generated is not in general. All right, that was major major contribution of Don Woody in this case, and then I can ask, without, I can mention two things. First, that finitely generated pro P group is not also is not accessible in general. But for finitely presented group, we have open question. All right. We don't know whether it is accessible or not. All right. And for in the abstract case, the geometric group theory was used in very essential way. All right. So geometry played very role with that we don't have in the pro P case for finitely presented group. And this there is complementary question that we don't know whether a finitely generated group, pro P group that acts on pro P tree with finite vertex stabilizers is accessible. And it is important because if it is accessible, then G is virtually free pro P. Means that it has subgroup of finite index which is free pro P. The problem is the following: that in the abstract case, all right, the stalling theory was involved to prove that if we have a virtually free group, then it splits. Now, if group acts with finite vertex stabilizers, right, then on a tree, it is automatically virtually free because it is in abstract case complete triviality. Why? Because our quotient graph can be assumed to be finite. And then we just miss all stabilizers, and that's it. By going to subgroup of finite index, and then group acting freely on a tree is free. Right? But in this case, it is not clear. Why? Because we cannot assume that our quotient graph is finite. But we could, right, if the group would be accessible. If the group were accessible, we could do it. Okay. This is complementary result, right, about accessibility, right? If group satisfy this this condition, namely that the space of n's of pro P group, right, is finitely generated as PG model, then G is accessible. This was proved by me and Zoe Chedidakis in one case and independently by Wilkes in the other case. All right. And then, well, there is open question whether converse is true in the pro P case, but in the abstract case it is. Okay. And now we come in question to generalized accessibility. Accessibility that I gave definition was over finite groups. All right, of the class of finite groups. But in principle, right, we can study accessibility property over any given family of groups. And it was studied in the abstract case by Bestvina and other. There are many papers on this subject. And by Sela as well. It is quite important subject is accessibility in the abstract case over given interesting families, right? Especially for hyperbolic groups as well, right? And but in pro P case, right, the generalized accessibility has more sort of additional reason to study it, because the main theorem for subgroups of Basel theory works for generalized accessible pro P groups. Why? Because, as I said, we can assume that if group is accessible, right, then the quotient graph is automatically finite. All right, so it works in this case. All right, so this is the reason to study, and then I come to acylindrical accessibility. Oh, what did I do? I went to my acylindrical accessibility. All right, acylindrical accessibility was studied by in the abstract case for geometric group theory by Sela. Right, and he proved that in this case acylindrical accessibility, but I have to say what means acylindrical. Group acts on a tree acylindrically if every geodesic of length k, right, has trivial stabilizer. All right. Example: if we have malnormal amalgamation, and group is malnormal if you have it has trivial intersection with every conjugate of it, right? Then it is one acylindrical, right? Zero acylindrical means that the H groups are trivial, not H group. Stabilizers of H's are trivial, right? One acylindrical means that stabilizers of H's is malnormal, right? If you assume that it is malnormal in one factor and no assumption on the second factor, it will become two acylindrical, right? And so on. So Seller proved the following, that any finitely generated group is acylindrically accessible, right? And I want to present here the Propi version of it that was obtained by Ilaria Castellana jointly with the speaker. So a finitely generated Propi group is k-acylindrically accessible. So it is Propi version, and here we even gave a bound for accessibility number, A of G. All right. And a very important corollary of this, as I mentioned, is this one, that subgroup theorem works for finitely generated subgroups of acylindrical Propi splitting. So in that case, Basser's theorem works in full strength, namely subgroup theorems are true. All right. Thomas, I'm not looking at time. It is, I think, your job. Okay. So just. And also, it gave as a corollary the Propi version of Kara's solitary result, right? That if we have free product of Propi groups with malnormal amalgamation, then every two generated subgroup, which is not conjugate to one of the factor, which is the generated case, is a free product of two cyclic groups. Cyclic accessibility. Cyclic accessibility also was studied by Ilya Rips and zalesskii, right? And it is cyclic accessibility in abstract case particularly important for hyperbolic groups. Why? Because in hyperbolic group, every maximal cyclic subgroup is malnormal. All right. So in Propi case, cyclic accessibility works for any finitely generated group without any restriction. We don't need to assume any malnormality, right? And this is a result obtained jointly with Deutsche, and we have even a number of accessibility. It's less or equal than 3D minus 2. However, in the abstract case, just with the contrast, we can contrast. I say that actually in the abstract case, group can be cyclically inaccessible. Why? Because Dan Woody-Jones constructed an example of group G that splits of a cyclic subgroup as itself. G, free product with amalgamation of a cyclic group with G itself. Then, of course, it is inaccessible because every G we can split further, and so on. All right. This is an important example, right? But limit groups are cyclically accessible, right? And Richard Weidman proved even this bound, which is, you see, in the abstract case, worse than our bound. All right, but still bound exists in the abstract case for limit groups. Open questions. Since we have many students with starting PhD, it is important to have many open questions. Let's come to profinite group. All right. The first question, is finitely generated profinite group accessible over trivial groups? All right. Now, well, what means over trivial group? That stabilizer, right? Stabilizers are trivial. H stabilizers are trivial. So if group acts on profinite tree with trivial H stabilizers, whether it is accessible. Right? And one can think, well, but then it is free product. I mean, what is the question? Well, not quite. The problem is the following: that for free profinite product, it is known that a number of factors cannot exceed the number of generators. It is in principle known for free product. The problem that in profinite case group that acts on the profinite tree with trivial edge stabilizers, right, is not obligatory free product, right? And in fact, it comes from a failure of profinite nature that comes from a notion of projective group. Schreier's theorem in profinite context is not true because not every subgroup of free profinite group is free. It is projective. All right. And similarly, Courage subgroup theorem also doesn't hold in the free profinite case. In the profinite case, why? Because subgroup of free profinite product is not obligatory free product. Right. Right. It is sort of projective. Or actually, it acts on the profinite tree with trivial edge stabilizers, but it is not a free product. So this question actually, how much time I have? Can I explain here more? Okay. Two. Then I'm not going to explain this. I just give this question. The second question, whether finitely generated profinite group are cylindrically accessible, but this is just generalization of our Pro-P result, and it is generalization of this question. All right. And for those who like analytic Pro-P groups, the question whether finitely generated Pro-P group is accessible over analytic Pro-P groups of bounded rank. All right. This is important, right? And then, since I have 2-3 minutes, I skip coherency, even if it is interesting, all right? And I come to, to this PDN groups, right? Pro-P PDN groups is Poincaré duality groups, all right? There's a big definition, right, about cohomological condition, but I'm not going to explain it too much because first I don't have time, and secondly, because it is, for those who do not know it, this definition wouldn't give really, all right? But the point is the following, that I want to present this theorem, all right, because it is starting point of the theory of GSJ decomposition. Because when we deal with accessibility, if group is accessible, right, then next step is to start to the theory of GSJ decomposition. And GSJ decomposition, it gives some kind of uniqueness of splitting, right? This splitting is not unique, but it treats some kind of uniqueness of the splitting. And GSJ decomposition came from manifolds. All right, it was a way of cutting manifolds into pieces such that they become free amalgamated product attention extension. And fundamental group of closed manifold is Poincaré duality group. All right, so that's why for Poincaré duality group this is important. And first decomposition of which is called GSJ decomposition in pure group theoretic terms for PDN group was proved by Peter Krapholler. All right, and here we are repeating, not repeating, sort of making Pro-P version of this. So this is can be considered two ways. First, as it is a Pro-P version of Peter Krapholler theorem for PDN Pro-P groups, and secondly, this is an initial step of GSJ decomposition theory for Pro-P groups.